Good morning, students. Today we will discuss Green's function for half space. So first of all, we define half space. Now the half space, which is open upper half space, this is the set of all n tuple type elements whose nth coordinate is positive and all the other coordinates are real numbers. This is called open upper half space, and the boundary of this half space, this is the set of all those points belonging to Euclidean space Rn whose nth coordinate is 0. So this is the boundary of this half space. Now, next we define the reflection of a point belonging to half space. So if we take a point x having the coordinates x1, x2, x3 up to xn, this is the point belonging to half space. Then its reflection in the boundary of half space, that is defined as the point whose nth coordinate becomes negative. And now because the nth coordinate is negative, so we can say that the reflection of the point x does not belong to the open upper half space. Now, to find Green's function for half space, first of all, we will have to find the corrector function. It means we have to prove that the function which we define by phi xy is equal to phi of y minus x bar. This function solves the boundary value problem. Laplacian of the corrector function phi x is equal to 0 in U, and its value on the boundary is equal to phi of y minus x, where this phi is fundamental solution of Laplace equation. So to solve this problem, let us define a function by phi xy is equal to phi of y minus x bar. Here x and y are the points of open upper half space. Now because y and x bar, they are n dimensional, the components of y are y1, y2, y3 and so on up to yn, and x bar is having the coordinates x1, x2, x3 and so on. Last coordinate is minus xn. Now substituting the values of y and x bar here, this function phi xy we have obtained. We can see that this function has singularity at x bar, but x bar does not belong to the open upper half space, and therefore we can say that the function defined by us has no singularity in open upper half space. Now, by definition of fundamental solution of Laplace equation, it is given by minus 1 upon 2 pi log of x mod for n is equal to 2, and for n greater than or equal to 3, this is defined as 1 upon n minus 2 alpha n into x mod raised to the power n minus 2. Replacing x by y minus x here, we get its value for n is equal to 2, which is given by minus 1 upon 2 pi log of y minus x mod, and for n greater than or equal to 3, it is defined by 1 upon n minus 2 alpha n y minus x mod raised to the power n minus 2. Now to prove that the function defined by us is corrector function, we will have to prove that for y belonging to the boundary of open upper half space, the value of the corrector function phi x at y, this is given by phi of y minus x. So to prove this, let us take y belonging to the boundary of half space. Now let us find y minus x bar. Substituting the values of y and x bar, the coordinates of this point becomes y1 minus x1, y2 minus x2 and so on. Last coordinate is xn because yn is 0, and also y minus x is having the coordinates y1 minus x1, y2 minus x2 and so on. Last coordinate is minus xn. If we find the magnitude of both vectors, we can say that their magnitude is same. And now by definition phi xy, this is defined by phi of y minus x bar. Substituting the value of this function here. Now using this result, because the magnitude of y minus x bar is same as the magnitude of y minus x. So we can replace the mod of y minus x bar by y minus x mod in both terms. So we can see that the value of function phi xy becomes phi of y minus x. Here this phi is fundamental solution of Laplace equation. So we have proved that if y belongs to the boundary of open upper half space, in that case the value of this function is phi of y minus x. So we can say that the function defined by us, that is the corrector function, are having no singularity in open upper half space. Now by using this definition, we can define Green's function for half space. By definition of Green's function, it is given by the difference of phi of y minus x with corrector function phi xy. This phi is fundamental solution of Laplace equation. Now for the half space, we have defined the corrector function by the formula phi of y minus x bar, where x and y, these are different points, and x bar is the reflection of point x in the boundary of open upper half space. So in this way we can define Green's function for half space. Now our next article is to solve the boundary value problem Laplacian of u is equal to 0 in the half space, and the value of function u on the boundary of half space, that is g. We are to find the solution of this boundary value problem. Now let us take the solution of this boundary value problem is denoted by u, which is twice continuously differentiable function defined on the open upper half space. Now we already find the solution of the boundary value problem for Poisson's equation. Poisson's equation is Laplacian of u is equal to minus f in u, and on the boundary the value of function u is g. This is boundary value problem for Poisson's equation. In the previous article, we obtained the solution of this problem, which is given by minus integral over boundary of u g into curl g by curl nu plus integral over the set u f of y into the Green's function g. Here the point x belongs to the set u. Now here, because f is 0, so in this formula this integral will become 0. So the solution of our given problem, that reduces to the form ux is equal to minus integral over the boundary of half space g curl g by curl nu. Here this nu is unit normal vector, which is a vector drawn outward to the open upper half space. Now in the half space, this unit vector nu, that is in the direction of minus yn. So curl g by curl nu, that becomes minus curl g by curl yn. Substituting the value of Green's function for half space, which we defined. Now to find curl g by curl nu, we require the derivatives of these two functions with respect to yn. So let us find them one by one and putting the value here. Now by definition of fundamental solution of Laplace equation phi of y minus x for n is equal to 2. This is defined by minus 1 upon 2 pi log of y minus x mod. And for n greater than or equal to 3, this is defined by 1 upon n minus 2 alpha n y minus x mod raised to the power n minus 2. Now, to find its derivative with respect to yn. By definition, for n is equal to 2, its derivative means the derivative of this term. Here, minus 1 upon 2 pi, that is constant, and derivative of this function, derivative of log of y minus x mod, this is 1 upon y minus x mod into the partial derivative of y minus x mod with respect to yn. Now the derivative of this term with respect to yn, that is given by yn minus xn upon y minus x mod. So putting the value here, we obtained this derivative for n is equal to 2. Now for n greater than or is equal to 3, let us find the derivative of this function with respect to yn. Now by definition of this function phi, for n greater than or equal to 3, its value is given by 1 upon n minus 2 alpha n y minus x mod raised to the power n minus 2. Now these three terms are constant. Derivative of 1 upon y minus x mod raised to the power n minus 2. Its derivative is given by minus n minus 2 upon y minus x mod raised to the power n minus 1 into the partial derivative of y minus x mod with respect to yn. And its value is yn minus xn upon y minus x mod. Now we can combine these two terms. So these two terms when combined becomes y minus x mod raised to the power n. Now we can combine these two derivatives. So in general, we can say that for n greater than or equal to 2, the partial derivative of this function with respect to yn, that is given by minus yn minus xn upon n alpha n y minus x mod raised to the power n. Similarly, we can find the partial derivative of this function with respect to yn. So in this derivative, because there is only the difference of negative sign in the nth coordinate of x and x bar, so the derivative in this case will become minus of yn plus xn upon n alpha n y minus x bar mod raised to the power n. Now we can substitute these two values in curl g by curl nu. After substituting the values, we get the value of this term, which is yn minus xn upon n alpha n y minus x mod raised to the power n minus yn plus xn upon n alpha n mod of y minus x bar raised to the power n. Now, because the mod of y minus x and y minus x bar, that is same for y belonging to the boundary, because in this case nth coordinate is 0. So we can substitute y minus x mod in place of this term in curl g by curl nu. So we get the value of curl g by curl nu, which is given by minus 2 times xn upon n alpha n y minus x mod raised to the power n. Now we can substitute the value of this partial derivative of g with respect to nu in the equation 1, which gives us the solution of our boundary value problem. So it is given by ux is equal to minus integral over the boundary gy into curl g by curl nu, which is minus 2 times xn upon n alpha n y minus x mod raised to the power n. these terms 2xn and alpha n. These are independent of y, so we can take these terms out of integral sign. So the value of function u can be written as 2xn upon n alpha n integral over the boundary of half space of the function gy upon y minus x mod raised to the power n. Here x belongs to the open upper half space. Now let us define Poisson's kernel for this half space. We have denoted it by k, which is a function of x and y. Poisson's kernel is defined as the function given by 2 times xn upon n alpha n y minus x mod raised to the power n. Here x belongs to the open upper half space and y belongs to its boundary. So this expression which we have defined, this is called Poisson's kernel for half space. So in terms of Poisson's kernel, we can write the solution of given boundary value problem, which is given by ux is equal to integral over the boundary of half space of the function gy into kxy. Kxy means Poisson's kernel. So this is the solution of given boundary value problem in terms of Poisson's kernel. And this formula, that is also known as Poisson's formula. So this was our topic, Green's function for the half space, and by using that to find the solution of the given boundary value problem.